All right, so I'm just making sure that everything is working. It's my first webinar. So I'll just start in a couple of minutes once I know everything is working fine. All right, everything looks fine to me. So I'll go ahead and start. All right, so this is part of our free webinar series. This webinar is about Catena, a high-performance time series storage engine. So a little bit about myself. My name is Preetam Jinka, and I'm an engineer at VividCortex, and I'm an undergrad math student at UVA. You can find me on Twitter, and there's my GitHub handle. I'll be talking about some code in this webinar, and you can find all of that on my GitHub page. And feel free to ask me questions on Twitter. Preferably after the webinar. I might get a notification during, and I may be able to answer it, but go ahead and use the YouTube comment section if you have any questions during the webinar, and I'll try to answer those. There is like a 30-second delay, so I might not see it immediately. So a few caveats. So there's a lot of information that can be covered, but it won't be, just because this is such an in-depth topic. There's a lot of things that you have to know. It's not just about databases, but storage engines. So there's lots of things that get involved. But I have some recommended prerequisites. It helps to know if you know what indexes are, especially in relational databases like MySQL. And I guess a vague understanding of write optimization versus read optimization. But I'll be covering some of that in future slides. And hopefully you've used some sort of key value storage library like LevelDB before. If you haven't, it would help to sort of know sort of some background information about it. If you don't, that's okay, because I have a list of resources at the end that you can refer to. And a recording of this webinar will be available, so you can, if you're not sure about something, you can refer to the resources at the end, and then come back and watch the recording again, and maybe you'll have a better understanding of what's covered. So I have a personal project called Cistern, which is a network flow collector. It's basically made for monitoring enterprise switches, routers, and servers. So basically, imagine a data center, and you wanted to monitor an entire data center, but you wanted to do it with just one program. So Cistern is meant to be a collector for all that flow data. So since it's a monitoring system, it sort of implies that there's time series metrics. And basically, the system that I'm going to describe here is used in Cistern to plot and store time series metrics. So it's actually used in something, and I'll sort of demonstrate how it's used. So I'd like to talk to you a little bit about the time series data at VividCortex. So Cistern is the project that I'm building this time series storage engine for, but it's inspired by a lot of the things that we do at VividCortex. So we'll just dig into that a little bit. So VividCortex is a monitoring company. We have web app, and you can view lots of different time series charts. So in this case, we're looking at MySQL commands for 4 different database hosts. and you can see those, the host descriptions basically, or the names following the chart title, and they're prefixed by a $sign. So as you can see, we have 4 different hosts, and we're looking at lots of different metrics that represent MySQL commands, and we're looking at a relatively short time range. So immediately, I hope you can look at this and sort of keep this in the back of your mind when I go through the other details, because there's a lot of characteristics in this picture that are going to come up later. So for example, you can see that when we're looking at time series charts in the web application, we're not looking at hundreds or thousands at a time. We're usually looking at very few time series metrics for very few sources. So in this case, we have like 4 sources or hosts. So we have systems that are emitting metrics, and in this case, we're looking at 4. And there's a few MySQL metrics that we're looking at, and there's also the time range that matters. So if you think about all of the parameters here, we have a source, and we have a bunch of metrics, and then we have a bunch of timestamps that we're looking at to plot these graphs. You'll notice that dbshard5 has a bunch of metric values that aren't really visible. They're either 0 or they just don't exist. So we'll get into the details about that shortly. So we store time series metrics and time series data in MySQL at VividCortex. Specifically, we store by default 1 minute worth of data per row. So we have a table with all of our time series observations, basically. And each row has 60 1-second resolution values for each metric. So we have this batching system with a compression technique and stuff like that. So we have another webinar available that you can view, and I listed that at the end. So you can watch that to learn more about how we store time series data in MySQL. But to summarize, we have tables with time series observations, and the columns are basically host, metric, timestamp, and then we have values. And our primary key is host, metric, timestamp. So we're using InnoDB. It's a B-tree-based storage engine. And something we do to make our tables operationally a little easier to manage is that we partition by time range and resolution. So we downsample older data. So instead of having 1-second resolution, we store it in 1 minute resolution. So that's sort of the background that we have to sort of approach this time series storage problem. So in terms of the actual operations that happen, inserts usually come in 1 minute batches. That's because we have agents that get installed on customer systems, and they batch up time series observations of lots of different metrics and send them to our API. So we obviously can't get an API request every second per server. That would probably take down our APIs before it hits the database. And we also monitor lots of metrics. So we try to monitor as much as we can on systems. So that means we end up with a lot of metrics. So usually we're getting fairly large payloads of 1 minute, 1 minute worth of observations for lots of different metrics. So that's for inserts. for queries, we're usually doing lots of range reads, and we're usually querying small subsets of metrics data, queried over varying time intervals. So if you remember back to the screenshot of the charts I showed you, a lot of our data is sort of requested like that. So we're either plotting stuff or doing analytics over these time series data. So metric names. So something interesting that we do that some systems have this method of adding tags to time series metrics. We actually don't use tags necessarily. What we do is we sort of encode tags into the metric name. So in this example, you see hosts, queries, C, and then you have this identifier, and then at the end you have tput. This is basically the throughput for query 137 whatever with the commit verb. So this is some sort of query, and we're looking at the throughput of commits. So our metric names are just strings, and they're separated by periods. And we have a certain format that we name our metrics, and they're sort of encoded with tags within them. So what's the consequence of this? Well, we end up with lots and lots of metrics. As you can imagine, each metric or each query that runs on a database server has its own ID, and for each query ID, we generate lots and lots of metrics. So we have lots of metrics, and that's high cardinality. The other consequence is that we get potentially sparse metrics. That means most metrics aren't present at all timestamps. So imagine this query that may only run once a day for a short time. So you only see values during that time, and you don't see many values. But you have to sort of know that it exists. May not make sense now, but when I get to RRDtool or Whisper, it'll make more sense. So to summarize important characteristics of our time series data, so we have high cardinality because we're monitoring all the things. We just have lots and lots of metrics to manage. And our time series are not just for charts on the web app. There's lots of different things that we can do with time series data. So that requires a few different workload characteristics that we need to be taking care of and looking into. And it also requires a lot of storage. Again, the metrics that we show and plot on the web application are just a few of all the metrics that we're actually collecting. So it's not just about being able to show plots on a website. We're actually interested in having as many time series metrics as possible so we can do lots of different analytics. So sparseness is the other characteristics that we're interested in. Because we're monitoring so many things, we might not know what to expect. So for example, if you think back to the query ID, there's lots of different ways of generating query IDs. We do it with a hash, basically. So we don't really know what kinds of metrics we're going to be getting on a database server. So if a customer starts sending us data, we have no idea what kinds of metrics that we're going to get. And we also don't know how frequent we're going to get them, just because it just depends on like the query workload and stuff like that. So when people talk about monitoring and time series databases, a few popular names come up. One is Whisper, and the other is RRDtool. So if you have, if you have web hosting at some hosting provider and they're showing you bandwidth charts, usually they're generating those with RRDtool. And Whisper is used by Graphite, also a popular monitoring tool. So these two systems are made for monitoring, not this guy, not the kind of monitoring that we do at VividCortex. And I'll explain why. So with Whisper, it uses a file per time series. And this simplifies the storage logic just because, if you have one file per time series, you can just open the file and, do what you need to. But this does not scale well. It simplifies the storage logic, but it's really pushing the problem somewhere else. Now it's like the file system's problem. Now, you end up with limited file descriptors. If you have lots and lots of metrics, you run out of file handles and things get difficult. Speaking of difficult, backups are also difficult because if you have a million files, it's just really hard operationally to deal with those. So RRDtool is a round-robin database, so it has a fixed size on disk. So you basically pre-specify what kinds of metrics you're going to get, and it pre-allocates that space on disk for you. So RRDtool is really best if you have observations coming in at regular intervals. And there's a reason why bandwidth providers or ISPs love to use this, because they know sort of what metrics they're collecting, and they can just pre-allocate. It's really simple, but it doesn't handle sparse metrics well. So what else can we do? So here are some observations. There are fast and scalable storage engines. Pick a database and it usually has some fast storage engine. For MySQL, you can look at NoDB and so on. There are also time series storage engines like RRDtool and Whisper, but they're not exactly fast or scalable. But they do have some operational benefits with time series data. Specifically like retention or downsampling and stuff like that. But there seems to be this big difference between high performance storage engines made for databases like Postgres, MongoDB, or MySQL. And then there's the other storage engines made for time series, but there seems to be this weird difference. Like, why not fast storage engines for time series? So because we're talking about storage, we need to think about, or high performance storage, we need to think about optimization. So because we store our time series metrics right now in MySQL, we have to think about the way we index and the way our tables are set up, our schemas. So the right optimized order would probably be something like timestamp, host, and then metric. If you're going to keep a table in order, it makes sense to sort of, if you want to make things right optimized, it sort of makes sense to keep them in the order that they arrive, so that you're not doing too much shuffling around. In this case, since we're dealing with time series data, it has this interesting characteristic that it's somewhat already ordered, right? Time goes one way, and our time series observations are time-stamped, and since they're coming in time order, it's already ordered by timestamp. So that seems to be a logical first choice for right optimization, to have the timestamp first. And then host and metric, well, you can always rearrange it somehow before you insert into a database. So I have an asterisk there because to assume that time series observations come in time order is not always a good idea, just because if you're expecting observations from two different sources, and one is halfway across the world and the other is right next to you, well, one sources timestamps might be a little bit behind in others. So can't really make that assumption, but we'll just sort of ignore it for now. But the read optimized order is really different. And so in this case, when we're, imagine you're on our web app and you're looking at time series charts for one of your servers, and you're just looking at like MySQL metrics. So in this case, you really want to filter by host first, and then metric, and then receive a timestamp values, just because you'd reduce the number of rows that you're looking at by eliminating most of the hosts first. So we have this big difference. We have the write optimized order and the read optimized order, and it looks like we're going to have to make some sort of trade-off. So before I get into that, here's the obvious question. Why not just use an existing system? Why not just use LevelDB or something? Or why not just use this B-tree library? And I think it's really important to reinvent wheels, not because there aren't good solutions already there, but it really teaches you a lot about existing systems. So why write a storage engine? Well, it teaches you a lot about the existing storage engines in a way that you can't really understand if you just sort of learn about them head on. Compression. So time series data compresses really well. Especially the kinds of data that we handle at VividCortex. So compression is really important, just because it's really easy to run out of space monitoring everything. We try to monitor as much as we can, but we have to be careful because we can really end up with too many things going into our systems, and it's just too much to handle. Compression makes a lot of sense for time series just because it has a fixed structure. It's highly repetitive, or it could be highly repetitive. So imagine a metric that's always constant. Perhaps you're monitoring swap usage on a server, and you always have lots of memory. So your swap usage is always constant and it's 0. So you're going to have all these zeros, but you might not necessarily want to throw that data away just because it's not changing. You want to have that stored, but you're getting the same values all the time. So it's sort of like it's begging to be compressed. And compression works really well with time series because time series data are written in access and continuous streams and ranges. If we're requesting a plot of data, it's usually in a sequential stream. And it sort of makes sense to use compression because intuitively it seems like it's a good option. So just a brief summary of best cases for reads from a storage system. So the fastest way to read from a disk is sequentially. So SSDs make things a little complicated, but in general, that's not a bad idea to assume that disks are best at doing I/O that's sequential. And we want to minimize the number of expensive disk seeks. This is a huge problem with spinning disks. Again, it's less of an issue with SSDs, but again, there are other reasons why sequential I/O is sort of preferred. And we also want to read only what we need. This goes back to sort of read optimizations. You don't want to read too many rows and just not use most of them. So in other words, we want to reduce the amount of read amplification. So writes are pretty similar. Writing to a disk sequentially is preferred, and it's usually the fastest. Again, different for SSDs, but we won't get too into that. It's better to write without reading. This is pretty important. And you'll see that oftentimes this is an issue, especially with B-tree-based storage engines, where you can't really read, you can't write a record without sort of reading the root and then a few levels down and figuring out where to put that data. And for writing, we really want to avoid rewriting data that do not change. If you think about time series observations, you have a system, you're observing it at different points in time, and you're sort of generating time series metrics. And once you observe something, it doesn't change. And it doesn't really make sense to rewrite things that don't change. So that's something that we have to think about when we're thinking about storing time series. It's that they usually don't change. So rewriting is also related to write amplification. And this is really important for SSDs that have sort of a limited amount of writes that they can do over their lifetime. So here's a quote that I picked out from Barron's State of the Storage Engine post. I think it sums it up pretty well. You can have sequential reads without amplification, sequential writes without amplification, or an immutable write-once design. You can pick any two. Now, yes, this is true, but I think if you sort of think about this a little bit, you sort of, again, it's all about trade-offs, and it's all about sort of picking the right parameters. So what if you say, okay, I would like sequential reads and sequential writes, but instead of write once, maybe write twice? Is that really that much worse than write once? So it's all about parameters and trade-offs, so keep that in mind. So here's a trivial storage technique. You're getting time series metrics, and you just want to trivially store them on a disk. And you can do that by just writing the data as they arrive. So I guess it could be in a timestamp metric order. So this is really fast for writes because you're doing sequential I/O, but it's not really helpful for reads, because let's say you wanted to plot a time series metric, a single time series metric over a range of timestamps. You really have to do basically a table scan through all your values, because you're not indexing by metric. So we need to think about indexes. So there are lots of different ways to build indexes, but I'll just concentrate on the two sort of well-known big categories with ordered key value data structures. So we have B trees on the one hand, and on the other hand, we have LSM, or log structured merge based designs. So B trees are generally read optimized. They're used by most relational database management systems, although that's appearing to change with what Facebook is doing with RocksDB and stuff. So B trees are, they've been around for a while. MySQL's InnoDB is a good example. LMDB is a very lightweight and interesting C-based key value store library. It's worth looking into, I think. There's BerkeleyDB, which is used by lots of different projects. It's pretty well known. And there's lots of others. So with LSM, it's generally write optimized. You have things like Cassandra's storage engine, LevelDB, RocksDB, lots of different types. And LSM has been a more recent development. I think people have been using it more with the SSDs, because it's sort of it's characteristics are better suited for SSDs. So in the beginning, I mentioned my personal project. So it's a monitoring system. It's written in Go. So when I was sort of starting out thinking about time series storage, I was really looking for something written in Go, just because it simplified sort of implementation and dropping it in and stuff like that. So there are two major options for Go programs. One is Bolt, which is based on LMDB that I just mentioned, and it uses a copy and write B tree. And as an interesting fact, InfluxDB now uses Bolt. So I'll make some comments on Bolt, and you can sort of extrapolate from there. So the other option is LevelDB, and it's an LSM-style storage engine. It's also a ordered key value storage engine. So both of these storage engines are built up on an ordered key value data structure. So in terms of the actual usage and interface, they're pretty similar, but they have pretty different performance characteristics. So there's lots of different types of B trees. There's lots of different implementation choices. You know, B tree storage engines are always in development, but we'll just sort of stick with copy on write B trees, just because they're a little simpler, and Bolt is based on this. And copy on write has interesting advantages. So here's a really brief diagram of what a copy on write B tree, how it works basically. So instead of modifying B tree pages in place on a storage device, copy and write B trees rewrite modified pages by sort of making a new copy. So as you can see, there are 3 different versions of the same tree, basically. And the black version is the one we're starting with. And the red version, we add I, the value I. And you'll see that the node containing G and H has to be copied and then modified. So we have, right next to the node with G and H, we have a new node with G, H, and I in red. And then because we changed that node, we have to update the parent that points to it. And because we can't update existing nodes, we have to make a new node for the parent. So that's why we sort of have AD and G in red and copied. Now, because we don't update pages in place, we can refer back to old ones if they haven't changed, because we know they won't change. So that's why the first 2 pointers are pointing back to the first 2 child nodes. And there's another modification, but I'll just skip that for now. So pros and cons of B trees. Number 1, they're generic, which means that they're really flexible. It's an ordered key value store. So you can basically implement any kind of data structure on top. And especially with copy on write B trees, they have great benefits like atomic hot backups. So that's really, really nice to have. And it's hard to implement something like that with another kind of data structure. The cons of B trees, well, because it's generic, it assumes more than what we need. We don't necessarily, for time series anyway, we don't necessarily need to modify existing data as much, if at all. So, that's something that we can do with a B tree, but we might not necessarily want that. Probably the big drawback with a B tree is that you have to do reads before writes. So, if you have to insert a new page without worrying about what's already in your database, you still have to read from the disk before doing any writes. So that's sort of a performance bottleneck. And some of the more abstract things, It's difficult to control page allocation on disk. I'm not saying it's impossible. I'm just saying it's sort of hard to control where your B tree pages are going to end up on a disk. So if you think about time series and sort of, how to lay those out, like how to lay out a bunch of time series points on a disk, generally you're not going to be thinking about splitting them up into pages and sort of randomly shuffling them all over a disk. That doesn't seem efficient, but it's really hard to control where your pages go just because of the way a B tree works. If you look at a copy and write B tree, just because each insert really appends new pages to the end, that might help if you're inserting in order, but we can't assume that. And generally, what happens with copy and write B trees is that there's a garbage collection mechanism to sort of reuse pages that aren't referred to anymore. So if you reuse pages that weren't in use, then you might end up with pages scattered all over the place. And if you're looking to do a linear scan of a bunch of time series values, you might actually be skipping around a lot on disk, which is not fast. So just a relevant snippet, you can look into optimize table, which is a MySQL command. It sort of talks about, if you look at the documentation, it talks about how to optimize the location of pages to improve performance. So the other issue with a B tree is that it's difficult to implement compression. So with something like Bolt, which is a simple copy and write B tree library in Go, it doesn't provide compression. That means you basically have to do it yourself. So if you don't do it yourself, you can rely on the library, but that makes the library really complicated. But if you had to do it yourself, it gets to be an operational and a programming sort of difficulty because compression really works well when you have large streams of data, depending on the kind of compression you use, obviously. But if you think about little 4K sized pages scattered all over the disk, it might not be that beneficial to compress those pages individually. And someone's just told me that it's a little out of focus. So maybe if I resize the window. Okay, let's try that. Hopefully this will make it just a little bit bigger. Okay, so with a B tree, it's also difficult to support concurrent writers, just because you have, it's a tree, you have a root, and it's really hard to sort of control a bunch of writers updating a tree if they all have to sort of contend on the root. So LevelDB. There's lots of different types of log-structured merged data structures, but I'm going to focus on LevelDB. So it's log structure. That means all updates are basically written to a log, and they're appended to the end of a log. So this is great because it's sequential I/O. And eventually, this log gets transformed into a sorted string table, which is as simple as it sounds. It's basically a file with a bunch of strings sorted in order, and they're compressed. So sounds good so far. I'm going to resize this a little bit more. Okay. So what also happens is older sorted string tables get merged together to form bigger sorted string tables. And the key space gets partitioned into multiple SSTs. It's partitioned by key. And basically what you end up with in the end is you have levels of SSTs. So here's a quick diagram, I guess, of LevelDB. So as you can see, writes get appended to the end of a log. And eventually the log gets transformed. All of the updates are reordered into a sorted string table. And eventually what you end up with is your entire key space, which is partitioned by these sorted string tables that are on different levels. And eventually they get merged into bigger and bigger levels with bigger and bigger sorted string tables. So you'll notice that the key space is partitioned, but I'll bring up why that's good and bad. It's good in the general case, but it's actually bad in the time series case. And I'll get into that now. So LevelDB is write optimized, so that's good. It supports concurrency, that's good. It also has compression, that's good. But the cons are it rewrites unchanging data too often, perhaps. So if you think about how many times a single time series point gets written, it might end up becoming really bad if you use LevelDB, depending on a bunch of parameters like how many keys you're inserting into the database and so on. The other con is that operationally getting rid of older time series points is actually kind of a hassle because LevelDB doesn't actually delete stuff immediately. So it does what's called tombstoning, which means it updates a record to show that it's been deleted, but it actually doesn't actually delete it. So SS tables. Partitioning the key space is great because we end up doing a lot less in terms of work to figure out where our key is when we're doing queries. But it's not so great with time series because we can't really control the partitioning specifically. Basically, intuitively, the way we partition time series data is we do it by time range, right? So maybe you want to partition by day or per hour or month, something like that. Because in that case, if you want to delete last month's data, all you have to do is drop the partition. But with LevelDB, because you can't really specify where SS tables get split, you can't just delete an SS table. So that's sort of an annoyance that we can't really fix easily. So I guess it's time to try something new, right? What about something that's optimized for fast concurrent writes, like LevelDB, optimized for fast bulk reads, sort of like a B tree and a lot like LevelDB, something that's operationally convenient for time series, something like Whisper or RRDtool, and something with powerful data access primitives. So basically, over the course of 2 weeks or so, I came up with a project called Catena, and it's similar to LevelDB. It has logs, compaction, support for concurrency and compression. It's also similar to a B tree with a hierarchy of extents of time series metrics and time series observations. It's implemented in Go because the parent project is written in Go. And it has a powerful data access primitive. So here's the API. It's really simple. And this is all you have to use Catena. You can create a new database handle, insert rows, which basically have a source timestamp, source metric timestamp and a value. And they're basically like simple structures. So you can insert an array of structs. And the only other thing you can do is create iterators. So I really like this quote by Paul Graham. Good design is simple. And this is a simple design, but it took a lot of work to implement this. So the overall design is that we have a bunch of partitions. So similar to how we store data in MySQL, you can partition data in Catena by giving it some sort of partition size. So for example, if you wanted to partition by hour and your timestamps represented seconds, you would choose a partition size of 3600. So data is automatically partitioned in Catena. So there's two kinds of partitions. There's a memory partition backed by a write-ahead log. This is a lot like how LevelDB does it. So there's a log that has all the recent updates, and then there's an in-memory structure that sort of keeps things indexed and in order. And there are also disk partitions, which are like SS tables. They're read-only, and they have compressed time series data, and it's memory mapped just for it's an implementation convenience, I guess. So here's how data is sort of structured in Catena. So we have partitions that have completely disjoint and separate time series data. So partitions are completely independent. They don't share anything. And this is operationally useful because if you have inter-partition dependencies, that might complicate some things. So in terms of what an actual partition looks like, I have a little diagram on the right. So you have hosts, metrics, and points. So in this case, I have two hosts, H1 and H2. They each have a few metrics. And for each metric, there's a bunch of points. You'll see that the number of points is not fixed, but there is a maximum size of the partition. And in terms of sort of the hierarchy of sources, metrics, and points, it sort of looks like this. In this case, I'm just showing the metrics for a single source and then the points for a single metric. But really, it looks like a giant tree. So this is where we get inspiration from a B tree. So internally, the partition list is actually implemented using a lock-free linked list. So this is really useful because every operation has to sort of access and query that linked list. And making it lock-free simplifies the implementation a lot because handling compaction asynchronously gets a lot easier with a lock-free linked list. So it's ordered by timestamp range. So the most recent partitions are at the head, and the older partitions are at the tail. So basically, because it's lock-free, the compactor, which operates on older partitions, can sort of stay at the end, and it doesn't grab a lock at the head where all the writes are going. And obviously, queries that are accessing lots of different partitions don't grab locks either. So that's a really useful implementation choice. So memory partitions are actually really simple. Apart from the write-ahead log, there's just maps for sources and metrics, and then have a slice of points for each metric. So just to make things a little easy to understand, I have this JSON-like diagram, I guess, that sort of shows you how data is structured in a memory partition. So in a memory partition, as the name suggests, everything is stored in memory. So there's basically a Go map that maps from a string to a source structure. And that source structure has a map from a string name to a metric structure. And the metric structure just has a bunch of slices that are backed by arrays, basically, that just store time series points. So disk partitions are a little bit different. In terms of the hierarchy, it's exactly the same, but the actual storage is different. So disk partitions are compressed. They basically have arrays of points stored side by side, as is shown here, with a bunch of metadata at the end, telling you where those arrays begin. And these arrays are stored compressed. So basically, you look at the metadata table, figure out which metric you want, which source and metric and so on. And you basically seek to the position that you want, and then start reading off data. So because it's compressed, you really have to read the entire stream, to access something. So if you wanted a point in the middle of the time range that D spans, you really have to start from the beginning and decompress up until there. So that's sort of an operational issue. It's not very useful. So the solution here is to split each of these arrays into smaller extents, and those extents are compressed individually. So really, a disk partition looks like this. It's a lot more complicated. So basically, there's a hierarchy of sources and metrics, just like the memory partition, except it's stored in a disk format. What happens is the metadata is actually stored in memory. And the metadata has all the sources and all the metrics, and for each metric, there is an array of extent data that stores the offset and the starting timestamp for each extent. So each one of these blocks represents an extent, and each color is supposed to represent a different metric. So if you wanted to look at the middle range of the first metric, you just have to figure out which extent it belongs to based on the starting timestamp, and then seek to that part of the file and then decompress the extent. So that's a lot better than having to decompress the entire partition width worth of compressed time series data for that metric. So extent compression considerations. So a really common approach is to store and retrieve data in terms of pages, because that's sort of how file systems handle data coming from a disk. But the problem with compression is that if you had 4K of uncompressed extent data, so here's a typo, it should be uncompressed, you really might not know how much it's going to be when it's compressed. So at this point, Catena does not do anything using page aligned I/O, just because I haven't really figured out how to do that efficiently yet. But that's something to think about. And the other issue is that if you're accessing an extent using an iterator, you really need to keep the entire uncompressed extent in memory, just because you're going to be seeking within that extent, and you have to sort of keep that entire thing uncompressed in memory. Otherwise, you would be decompressing the entire thing, getting a value, and then getting rid of it, basically. And then you're going to have to do that again every time you incremented the iterator. So what if two iterators have, they're looking at the same extent? Well, right now, the implementation requires them to each store a copy of the entire extent. This is sort of unnecessary because those extents are on disk partitions, which are read-only. So it makes sense to share that data. And that sort of means you have to have a system that's managing these extents. It also relates to, what if you have an extent that's accessed really frequently? Instead of uncompressing it and then reading it into memory and then sort of doing that over and over, why not just cache it, right? The thing is, caching extents, it's a whole nother data structure. It gets complicated really quickly. So I mentioned iterators, so I'll sort of go into detail about iterators. So iterators are the only way you can access time series points from Catena. So iterators are, you can safely use multiple iterators over a single Catena instance, and you can use those concurrently. And the really important thing is that they seamlessly transition across partitions. So even if you have 10 iterators across your entire database, they can be moving across partitions. They can move across extents and jump around, and that's all thread safe. So that's in the beginning I showed you the API. There's only a few functions or methods that you can use, but really behind the scenes there's lots of stuff going on. Lots of precise locking to make sure that if you're updating data in memory, that an iterator won't sort of mess with that. So everything's kept consistent. Iterators are also very composable. So internally, the implementation has different iterators for each partition. So a memory partition has a different type of iterator, and a disk partition has its own type of iterator. And the iterators that you use directly through the API, those are actually composed of sub-iterators that handle the complicated sort of logic of transitioning across partitions. So here's an idea. If you had a bunch of Catena instances that have different resolutions of time series points. So instead of having 1 point per second, if you had 1 minute, if you had each point representing 1 minute, it might be interesting to compose two different iterators that access data across these Catena instances. So here's how files look on disk. As I mentioned, disk partitions are read-only, they're memory mapped. So all of these files that end in .part are disk partitions. So there's over 400 files on disk in this example. You can't see them, but there are also a couple of write-ahead logs for the in-memory partitions. So as you can see, there's lots of files on disk, and the total space is less than 700 megabytes. So the reason why there are so many files is that I like to keep my partitions small. So in this case, I think they're only an hour. And that's because my little DigitalOcean droplet doesn't have that much RAM. So it only has half a gigabyte of memory. So I really need to make sure that I stay under, just so I don't run out of memory. So the issue here is that because partitions roll over really quickly, you end up with lots of files. And this is why LevelDB compacts older partitions. It's because you don't end up with lots and lots of files to manage. But in my case, I really don't want to rewrite a bunch of partitions because nothing is changing in them because they're read-only. But again, that's another trade-off. Maybe it's okay to rewrite them just one more time, just to save some overhead. So just to wrap things up, storage engines are really hard. It's very easy to make Catena consume all your RAM, just because there's no real limit on the number of the number of points that you can store in a memory partition, it's only limited by the range of timestamps, but it doesn't depend on the number of metrics that you're putting in. So if you had 1 billion metrics that each inserted 1 timestamp, you might run out of memory, and it's not going to do anything for you. The other issue is that it's not rigorously tested, just because it takes a lot of time. It takes a lot of time to write benchmarks. And it takes a long time to sort of figure out how to write good benchmarks that reflect different workloads. So there's, I have a lot of respect for people who write benchmarks because it's really difficult. And the other issue is that it has been implemented as it was designed. So for example, we didn't have extents until I started working on it during the second week. So I had 1 week when I sort of wrote the entire thing, and then found out about all these different issues, and then took another week to just rewrite it. So that's when the extents were introduced. So this takes a lot of time. So whenever there's a different design change, usually that requires re-implementation, just because, for example, introducing extents meant that I had to implement all of the serialization and deserialization, just because the formats changed. And because of that, I sort of lost all my existing data. So there's a lot of inertia there. And something else that's that has come up when I was testing this is that having back pressure is a really good thing. And you'll see this in a few blog posts all over the internet where people start benchmarking something and it's really, really fast in the beginning, but then they either run out of memory or run out of some sort of resources, and basically short-term benchmarks don't really reflect long-term efficient data storage. So for example, in Catena, there's a compactor that sort of follows behind and compacts partitions as they get older, but there's absolutely no back pressure on the rate of inbound writes. So you can keep writing to it, and you'll start accumulating all of these in-memory partitions as they roll over. But the compactor can't keep up because it's single-threaded, and compaction takes resources, and it's a lot harder to compress and compact data than it is to just write to the end of a log. So what ends up happening is you basically have lots and lots of in-memory partitions, and you run out of memory really quickly. So back pressure is really important. So that's something to keep in mind when you're not just looking at Catena, but also other storage engines. So what does high performance mean? So we said that this is a high performance storage engine, but what does that really mean? Is it really about write throughput? Because if you think about back pressure, if you think high performance means the highest write performance at any given time, well, I don't really think it's a good thing, because if you don't have back pressure to sort of artificially slow down writes, you're not going to have a system that's scalable or stable over time. In addition, if you're just focused on writes, what about reads? Because if you're writing a lot and you also have concurrent readers, is that going to slow your system down? Is that high performance? In a time series database, I think it's really important to think about reads too, because yes, we're getting lots of inbound time series data, but we also have reads that are happening at the same time. So we're always going to have writes just because these systems are emitting metrics. But occasionally we have these really intensive reads. So what about read throughput? So if the goal to have high performance is lots of read throughput, well, if it's not fast enough to accept all the writes, then what good is it to have great read throughput, right? So it's all about this trade-off. Concurrency. So there are some systems that, for example, Bolt that's used in InfluxDB can only have one writer. So is that high performance? Well, it can accept writes really fast, and it's also really great for reads, but concurrently, we don't really know, right? So it's all about resource management too. So suppose you had, if you had one file per metric, yes, it's going to be really fast. And if you're appending to each one of those files, sure, it's lots of sequential I/O, and you might get sequential reads too. But is that really good use of resources? Maybe not. So there are always trade-offs, and I think performance depends on context, because just because something is really performant for one company or individual or system doesn't mean it's always performant for something else. So just a few closing thoughts. Catena is just a prototype. Somebody mentioned that the phrase "learning in public," and I think that expresses this quite well. So this is just me learning in public and trying different things out. It's not really meant for production use, just because it doesn't make good use of RAM, for example. There are no limits to keep things safe. So if you're using a production database system, there's a whole team of engineers working on those kinds of problems to make sure that data stays safe and you won't run out of resources. And it sort of handles lots of different workloads. So something like that is something like DB is totally different from Catena, which is made by a college student over a week. So keep that in mind. And overall, high performance time series storage, I don't think this is a solved problem yet. Having a prototype is great because you get to look at lots of different problems that come up in the implementation. But overall, obviously what I have is just a prototype, but I think it's still an unsolved problem. So here are a bunch of resources that you can use. So if you didn't understand something or something was a little fuzzy, I recommend that you go through these resources because they really give you a good overview of indexes, B-trees, log-structured merge trees, fractal trees, concurrent programming, B-trees, lots of different things. So the webinar is recorded, so you can go ahead and read through these and then come back and rewatch the webinar and hopefully get a better understanding of what's going on. So that about wraps it up. Feel free to contact me. I'm on Twitter. You can also tweet to VividCortex, and there's my email address. So I'll be looking at the YouTube comments for a few minutes in case there are questions. So I see that several people had the wrong time on the calendars. I don't know if that's an issue with something that we sent out, or if that was just a mistake on your part. I'll forward that on. All right, so I don't think there are any more questions. So I'll just wrap up now. So thanks again for joining. I hope you view our other webinars coming up soon.